This is another one of our periodic trends we need to identify and justify. There are exceptions to the generalizations, a lot more so than there is in electronegativity. Okay, there are some very standout exceptions to the rules, particularly looking at beryllium and boron, two neighbouring elements in the same period, and looking at nitrogen and oxygen, again, two elements in the same period. You must be able to explain them, and they are different reasons for each of them. For that, you need to know what first ionisation energy is, and you need to know what factors affect it. So we're going to go through that. So the first thing is, this thing in purple is its definition, or the writing in blue is its definition. They are equally valid. But if you miss something from either of them, you get it wrong. So here are the key points. One is, whatever element it is, sodium, lithium, chlorine, phosphorus, whatever it is, must be a single atom, which shows 1 mole of it, and it must be in the gaseous state, so you must use the subscript. It must be in the gaseous state to start with, because we don't want to waste energy taking it from solid to liquid to gas and then remove the electrons. If we start at the gaseous state, we have the atom, even if it's sodium, to then remove an electron off it, and we're only finding that energy requirement. This is the next thing. You must have an enthalpy change greater than 0. This shows that energy is required. You are putting energy in, because what we're looking at is how much energy is required to remove that electron, and why do some atoms have lower values or higher values than others. So you're comparing and contrasting different atoms, often in the same period, or justifying a trend. You'll notice I've got my electron in there. You'll notice I've got X plus being made, even if this is chlorine. Now, chlorine naturally makes a Cl minus ion. Don't get confused. For ionisation energy, it must be Cl plus in the gaseous state. So it must be a positive ion, even if they naturally make negative ions. That's not what we're looking at. We're looking at actually ripping an electron off, regardless of what it would naturally want to do. What affects it? Identical to electronegativity. But you need to understand your p-s orbitals a little better to justify ionisation energy. There's a bit more precision needed to talk about ionisation energy than with electronegativity. In particular is the second one. Okay, so I'm just going to quickly talk about effective nuclear charge. Again, we know what factors affect that. If everything's in the same period, more protons means a larger effective nuclear charge. Okay, because there's more protons and no increase in shielding. As you go down the periodic table, of course, you're going to get an increase in shielding, so therefore you're going to get a decrease in effective nuclear charge. You're also going to get a much larger radius. However, what you do need to be aware of is that the p orbitals are a little bit further away from the nucleus than the s orbitals. Therefore, it's a little bit easier to remove electrons from a p orbital than an s. So when we go from beryllium to boron, so boron has this electron configuration, 1s2, 2s2, 2p1. This electron is a little bit further away from the nucleus than these ones, so it's a bit easier to take off. So this has actually got a lower than expected first ionisation energy.
Is that the same with any p orbital?
Yes, it is. Of the same energy level. So the question was, is it the same for any p orbitals? Yes, so long as the number in front's the same. Okay? So to remove this one is a bit easier than it is to remove berylliums. Beryllium has a higher value, and it's because it's 1s2, 2s2. You'd expect it to have a lower value because its nuclear charge is smaller, 5 versus 4 protons. Okay? So you'd expect this has got a higher effective nuclear charge. However, the p orbital is a bit further away, so it's easier to remove than the s orbital. Okay, so just be aware, radius has a huge impact on ionisation energy. Huge impact. For another reason, nitrogen and oxygen are worth noting. All right, so nitrogen is 1s2, 2s2, 2p3. that 2p3 is a half-filled orbital, whereas oxygen is 2p4. You would expect with this only having 7 protons and this having 8, that oxygen should be a much higher value, but it's lower. And the reason is once I start pairing up the p electrons in the orbital, so if I just look at the p orbitals orbital diagram, they would have maximum spin. Every orbital in the p has only got 1 electron in each, so they can actually be quite close together, quite stable. Whereas here, one of them is paired up, and this means that the orbital takes up a bit more space. So there's a lot more electric repulsion happening in there, so it's a little bit easier to push that electron off. So a little bit less energy is required to make that happen. These are two very important exceptions if I look at the second the second period on the periodic table. However, the general trend is because nuclear charge increases and because generally the radius gets smaller, then you would expect the generalisation to be that as we go across a period, ionisation energy increases. And as we go down a group, because radius gets so much bigger, then ionisation energy gets smaller. This helps us explain things like why potassium explodes in water, whereas sodium catches fire and might blow up if we're lucky, and lithium just fizzes around like a little jet boat. Okay? The ease at which that electron can be removed, it's coming off a lot easier for this potassium because not much energy is required for it to lose that least tightly held electron. And therefore it's got a faster reaction rate in that case, and therefore it blows up. The other thing I do want to talk about is for those who are pushing on to excellence, sorry, not excellence, to scholarship stuff, there are second ionisation energies and third, and these can be used, or have been used and are used, to infer the electron configurations of elements. These numbers are always bigger than the one before them, okay? They're always bigger. It always takes more and more energy to remove more and more electrons. Because as you remove electrons, the electron cloud gets smaller and smaller because there's less electron repulsion. So it must get harder and harder to remove the next electron and the next one and the next one. When we see a dramatic jump, about something like 1,000 kilojoules per mole, for example, a really big jump, that infers that we've gone to a completely new energy level. So that's how we've sort of worked out our electron energy levels, or our shells, to help us understand how our electrons are arranged. This is one of the most important pieces of data that we use to work out atomic structure. Conversely, though, for you this year, we're saying use your understanding of atomic structure to justify the trends or the data you're given in ionisation energy. Any other questions on that?